All right, so now we're going to talk about systems of equations and how to solve them. And graphically, I just want to mention that we could solve these systems and look for where two lines intersect. But in this section, we're going to focus on algebraic methods. The first is substitution, and then the second algebraic method is called the addition or elimination method. Usually those are going to be a little more efficient for solving these systems. But graphically, if we were to graph our two lines, the point where the two lines intersect would be the algebraic solution that we come up with. All right, so the first method we're going to look at is the substitution method. So as we read through the steps, I'll apply them to number one. So first it says solve for either x or y in one of the equations. Now the mistake that most students make here is they read that and what they hear is solve the first equation for y, which isn't your only option. You actually have four options. You can solve the first equation for x, the first for y, the second equation for x, or the second equation for y. And you guys are just used to solving for y. You've done it for slope-intercept form for so long that you just kind of do it like a robot. So in this case, if we solve the first equation for y, you would subtract 5x from both sides and divide by 4, and you would have y equals, what, negative 5 over 4x plus 13 over 4. And then that's what you would have to substitute into the second equation. So where y is, you would replace y with that expression on the right. And you could do it and you could get the right answer, but you're dealing with all these weird fractions that you don't need to mess with. So there's an easier way. So don't do that. Don't make that mistake. Instead, make it easy. Look for the easiest way to accomplish that first step. So looking at these two equations, I see in the second equation, it just says x minus 2y equals negative 3. It's going to be super easy to solve for x. So I'm just going to add 2y to both sides, and that gives me x equals 2y minus 3. No fractions, no ugly weird numbers. This looks great. So step 2, now I'm going to substitute this expression into the other equation. So that means I need to take the other equation, in this case the first equation, and where it says x, I'm going to replace that with 2y minus 3. So I'm going to rewrite that top equation as 5, and then I'm going to replace x in just a moment, so 5 times x, but I'm going to substitute that, and then plus 4y equals 13. Now I'm going to replace x with the equivalent 2y minus 3 from that first equation, right? All right, and now, I'm not going to make that mistake, so I'm just erasing that. So now at this point, I can take that top equation and I can solve it for y. It's only written in y, so I can go ahead and distribute that 5. This gives me 10y minus 15, and then plus 4y equals 13. 10y plus 4y gives me 14y. And then while I'm at it, let me go ahead and add 15 to both sides. So I have 14y equals 28. Divide both sides by 14. And I solve and get y equals 2. So when I solve these systems, I'm solving for both x and y. So what I just learned is that my y-coordinate in my ordered pair solution is 2. So that's my y-coordinate, but I still need to find my x-coordinate. So I substituted, I solved the equation, and now it says substitute the value you found for x or y back into the original equation. So we know that y equals 2, and we can plug y equals 2 into this top equation, or we can put it in this bottom equation, or actually, I like to use this guy when we create that first substitution equation. I like to use that to plug in this known value. The reason is when we plug in x equals 2 times 2 for y minus 3 equals 4 minus 3. So at this point I have just that x equals 1. So it'll be a little bit easier and more efficient to solve that equation for the remaining variable. So I like to use that one. So we get the ordered pair solution 1, 2. And remember, because you are solving for x and y, you write your ordered pair solution, both x and y, in your answer. All right, and graphically, if we were to graph these two, this is the point at which they would intersect with each other. All right, so let's do this again using the substitution method for number 2. So first I want to make my life easy, and I see that we have this plus y in the second equation. So I'm going to take that second equation and solve it for y. Solve it for y by subtracting 2x from both sides. So this gives me y equals negative 2x minus 4. And now because I did that with the second equation, I'm going to take the first equation and replace y with 3x plus 2 times, and then in place of y, there's my equals negative 5 on the right side. In place of y, I'm going to replace that with negative 2x minus 4. And now, in that equation, I just have that equation written in terms of x, so I can solve for x. So I'm going to go ahead and distribute to get 3x and then minus 4x and minus 8 equals negative 5, so distributing that plus 2. 3x minus 4x gives me negative x. And then just to save space, I'll go ahead and add the 8 to both sides. So negative x equals positive 3. The negative 5 plus 8 is positive 3. Divide both sides by negative 1. So I solve and get x equals negative 3. So in my ordered pair solution, I know my x coordinate is negative 3. Now I need to solve for y. And I can use any of these equations. I could plug in x equals negative 3 here, or I could plug in x equals negative 3 here. But I like to use this guy. So that first time when I created that little substitution equation, to me that's the easiest one to use because it's already solved for y. So now we have y equals negative 2 times negative 3 for x minus 4, which is positive 6 minus 4, which gives me positive 2. So now I have the ordered pair negative 3, 2. And again, graphically, this is where my lines would intersect. So if I were to solve these two equations for y in order to graph them, this top equation I would solve and get y equals negative 3 halves x minus 5 halves. And the bottom equation, just subtracting 2x, I would get y equals negative 2x minus 4. So if I graph those two, and that's what I've done up here, I've got y equals negative 3 halves x minus 5 halves for my top one, y equals negative 2x minus 4 for my bottom equation. If I graph these two, you can see I'm going to use the trace function. So I'm going to click trace and then type in x equals negative 3, so negative 3 for x. And you can see that that point is where the two lines intersect. So for both y sub 1 and y sub 2, I get a y value of positive 2. So that's where visually the two lines intersect. So we solved for that algebraically. We can also see that happening on our graph. Okay, so for number 3, again, we want to use this substitution method. And the nice thing about number 3 is we've already got an equation solved for y equals 3x minus 2. So now I'm just going to take my second equation, 15x minus 5y equals 10, and I'm going to replace y with its equivalent 3x minus 2. So 15x minus 5, and then I'll replace y. I'll substitute that in, equals 10. So I'm going to substitute in 3x minus 2. Now my equation just has x in it, so I'll distribute. So minus 15x and then plus 10 equals 10. So on the left, 15x minus 15x, that actually adds up to 0, plus 10 equals 10. And 0 plus 10, of course, is 10 equals 10. So this is looking weird, right? So we've got 10 equals 10. So a couple of things that I want you to notice. First, really important, is there are no more variables, right? So before, after we perform this substitution step, we were able to get something like x equals negative 3, for example. When I have 10 equals 10, there's no longer a variable to solve for. So there are two things that I want to look for. When I have a statement with no variables like 10 equals 10, it's either going to be a true statement or it's going to be a false statement. If it's a true statement, then I say that I have infinitely many solutions. And if it's a false statement, I say I have no solution. And in this case, 10 equals 10 is a true statement. So I'm going to say that I have infinitely many solutions. So this true statement indicates that the system has infinitely many solutions. Okay, so that's my answer. Instead of having one ordered pair as my answer, now I have an infinite number of solutions as my answer. So let's get a little more specific here and see why this is happening. So my first equation, I can see that I've got y equals 3x minus 2, right? So let me go ahead and graph that. Y equals 3x minus 2. So that's what that line would look like. So y-intercept of 0, -2, and then a positive 3 slope. And then if I were to solve my second equation for y, so minus 15x, this gives me -5y equals -15x plus 10. If I divide all the way across by -5, this gives me y equals positive 3x minus 2. So obviously that should look familiar. That's the first equation that we had. So if I graph my second one, which is identical, y equals 3x minus 2, the red line falls completely on top of the blue line. Okay? So remember that solutions to systems of equations are wherever the two lines intersect. Oops, I can't spell. Intersect. Let's try this again. So wherever the two lines intersect. So intersection point or points equal my solution or solutions. Okay, so let's list some intersection points. So using the trace function, these lines intersect at 0, -2 because they're the same line. They intersect at 1, 1 because they're the same point. They intersect at 2, 4 because they're the same point, or they're the same line. And I could do this all day, literally until I die, because there are an infinite number of points where these lines intersect at, right? So that's what we mean when we say there are infinitely many solutions. It's not enough to say any real number is a solution or any point is a solution, because, for example, they don't intersect at 2, 0, right? That would not be a solution. So it's not that they intersect all over the place at any point, but any point that falls on that same identical line is a solution to the system of equations. So we could get more specific and write our answer in set builder notation. So that's those squiggly braces. So we could say any solution xy, any ordered pair xy, such that, and then we could write, for example, this relationship, y equals 3x minus 2. That's another way to get a little more specific about the fact that we have infinitely many solutions. Any ordered pair xy that satisfies that relationship, y equals 3x minus 2, any ordered pair that falls on that line would be one of our infinitely many solutions for this system.